Alright guys, this is pre-calculus 324. We're going to be finishing off our area under the curve stuff here today. So it's an idea that we're going to keep doing, but this is the last our kind of introductory part of it before we can move forward to the next chapter where we're going to use it a little bit more intensely. So problem 130, we're talking about the population of San Tokyo, and they have a very high growth rate. And it is actually increasing, so they can represent that by the function 2 raised to the x power. So what we want to do is we want to sketch a graph of the function, and then break up the region between 2 and 4 into 5 intervals, just like we did the last time, and then go ahead and work through the problem in the same way as we tried last time. So go ahead and pause video, work through A through G here. It should be very similar to what we did in 323. So if you want to reference that as a point of what do I do, go ahead and do that. But then unpause and come back here and we'll go over that. All right, so if we want to sketch the graph of this, let me pull up my document camera. All right, just a real simple graph here. It should, being exponential, kind of do something like that, right? And it doesn't need to be perfect because we're not trying to make it an exact graph here. But I'm trying to find the region right there effectively, right? So I'll kind of shade all that. That's what I'm looking for. Okay. So what's going to be the width of each of these rectangles, right? So I'm looking for 5 left end points. So this distance here is 2. So if I just do 2 and divide it by 5, I'm going to get 0.2 as the distance here. So this would be 2.2, or 4, sorry, it's going to be 0.4, because it's 2. So 2.4, 0.8, 3.2, 3.6, and then 4. So if I kind of zoom in here on what I actually care about, I'm going to have 2 to 2.4 to 2.8 to 3.2 to 3.6 to 4. So those are going to be the kind of points that I care about here. So there's my first, second, third, fourth, and fifth rectangles, right? And I also know that I'm doing left end points here. Sorry, this is, I should label these as my x naughts because I'm getting a little bit ahead of myself here. So here's my x0, x1, x2, x3, x4, and x5. All right, so we can so then on part D here, why can left endpoint rectangles at a approximation of the area be expressed by 0.4 times 2 squared plus 2 raised to 2.4 plus etc. up to 2 raised to the 3.6. Okay. So effectively they're just saying, hey, here's what that sum is, and then we're going to actually write the summation for it. So that 0.4 ends up being our width of each of these rectangles, right? So if I look at this rectangle here that I will eventually be using, right? Its width is that 0.4, and that's consistent for every single rectangle that I'm going to be using. But then the height is going to be what's going to be changing, and I find the height by plugging in the x value into 2 raised to the x power. Right? So since my area is just length times width, it's that 0.4 times the response of this, and each one of those rectangles is going to have that 0.4 in front of it. So what they're effectively doing, let me pull it up so you can see a little better. What they're effectively doing here is just factoring out that 0.4 from all those and saying, well, it's 0.4, here's my width times all of these individual heights going across here. So hopping back over here, if I want to go down to the part where I'm trying to write a summation for it, well, my summation, I'm going to have 0.4 times my summation. And I want to follow the pattern here. I'm going up by 0.4, so that's 0.4x, right? And I'm starting at 2, so plus 2. That is the linear equation that I want to have plugged into my actual function. So that is what A allows me to count by point fours and tells me where I actually want to start. This tells me the pattern that will give me my actual height. So the sum is 2 raised to the 0.4x plus 2 power. Right? So now where do I want to do that from? Well, I want to start at my 0th term. So x equals 0. And I want to stop at my 4th term because I'm looking for left endpoints. And that would be the summation that will do that 0.4 times 2 raised to the 2 plus 2 raised to the 2.4, etc. equation for me. So let's figure out what our answer is. Or these are a approximation of that answer. So if I pull out my graphing calculator, right, again, we go to math, 0 for the summation. We want to do x from 0 to 4. And our equation is 2 raised to the, in parentheses, 0.4x plus 2. Right. And I can take that summation and I want to multiply it by 0.4 because that's going to be my width. And I get 15.023. So there's going to be the area for me. All right, let's go back over here. All right, so is your A approximation an underestimate or an overestimate for the actual area under your curve? So again, we can use those kind of rules of, well, if it's increasing, then left endpoints are underestimates. But in general, if you just look at the graph, you kind of want to sketch at least a basic picture of all of these graphs. When I do that, I see that, well, I'm under where my graph actually is. So I'm going to have myself an underestimate because I'm missing all of these little gaps here. I'm not getting that area, or that area, or that area, or that area, or that area. I'm missing all those darker black portions, right? So I'm not getting all of the area that I need. So it's going to be an underestimate for me. If I did a right end point, I would be above all of them. That would be an overestimate. So the one you want is kind of going to be depending on the problem. But in general, you would kind of do both and say, well, it's going to be between here and here. And the kind of narrower we are able to get that, the better. All right. So let's head on to the next one here. So go ahead and pause, try 131. This is going to be kind of much more of a less step-by-step hand-holdy kind of thing and say, hey, you've done this a few times. Can you do it entirely from scratch here? Right? So we're going to do 131 and then come back here and we'll go through it. Okay, so we have the paper airplane and we have its equation of 0.5 raised to the t plus 4. So if we sketch a graph of that, well, that 0.5 raised to the t should be an exponential decay function, and the plus 4 is going to raise it up. So it'll actually be looking, if I pull up my, there we go. We'll go ahead and graph it real quick, take stuff out. And we're going to be looking at 0.5 raised to the x plus 4. And we'll do zoom standard. So that's what our graph ends up looking like, right? So pretty basic if we want to go and sketch that. Just so we can have a better thing. When we draw this, it'll say it looks kind of like that. Again, your sketches don't need to be perfect. Kind of the important thing is that you have a general shape, especially if it's increasing or if it's decreasing. Right? And then we're looking at this over the course of, is it 4 seconds? Plane had 4 seconds flight. Yep. So we want to go 0 to 4 seconds. So 1, 2, 3, 4. We'll call it. All right. So if you think about what we're actually finding here, right? We're going to be finding the area between 0 and 4, or at least we're trying to estimate what that area is. So what that area would actually tell us is, well, this is time in seconds. This is my velocity in its feet per second. So what is my area as far as units go? Well, feet per second times seconds, the seconds cancel. This is feet. So the area here is the distance that my airplane travels in 4 seconds, right? So basically what I'm trying to find is if the area here is less than 17.5 feet, because that's how far away Mrs. Lori is from the start of the flight. If this area is less than 17.5, then it doesn't hit her, right? If it's more, then it does hit her, right? So then we gotta say, well, do we want an overestimate here, or do we want an underestimate here? So if we do an underestimate and we get less than 17.5, that doesn't really help us a bunch, right? Because we could still be over, right? If I get, well, I got 16.9 feet, but I know it's an underestimate, well, that's kind of ambiguous as to if it hits her or not. But if I do an overestimate, and that is 17.2, well, then I know it has to be under it, and it doesn't hit, right? But by the same vein, if I do an underestimate and I'm higher than 17.5, then I know that it will hit as well. But so you'll have a reason why you want to pick one. I'm going to go for an overestimate just so that I can probably predict that it's going to not happen. Let's go ahead and try that out. So I do not believe they tell us exactly the number of breaks that we want to use. So we can kind of use whatever we want, right? So the smaller those breaks, the better though, right? So let's first do one with a width of 0.5, right? So we'll do 0, and then we have 0.5, then 1, then 1.5, then 2, then 2.5, then 3, then 3.5, and then 4. All right, so here's my x naught, x1, x2, etc. Right, this is 0.5. Right, I don't need to label all of them because I just really need to get the idea of how those are being spaced apart. So to get my kind of linear portion, which models me counting by these, I'm going to be counting by 0.5s. Again, you can count by whatever you want. I'm going to count by 0.5, so that's my rate. So that times x plus where I'm going to start. And I'm going to start at 0, so I can just be 0. Right? So that is what I need to plug into my actual equation. Now the equation of this function is 0.5 raised to the t plus 4. So I'm going to plug this in for that t. This is how I get my t values that I'm going to be plugging in. All right. So what I'm going to actually be doing the summation of is 0.5 raised to the 0.5x. I really don't need that plus 0, so I'll just leave it off. Plus 4. So that's what I'm going to be doing my summation of. Now I'll do that starting from 0 and going till where? Well, this is going to be 0, 1, 2, 3, 4, 5, 6, 7. Right? Because I don't want to go to 4. I mean, sorry, if I go to my 8th term, which is 2, 4, this is the kind of error that a lot of people make. That ends up giving me an extra rectangle, and that left end point would actually be right over here. So I'm going to be getting way more than I need, right? So I don't want to be doing that. So this gives me all of my different heights, all being added up. I want to multiply that by my widths. My widths are 0.5. Let's see what we get. All right, so if I go back here, I want 0.5 times my summation, which I go math, 0. I want values of x from 0 to 7, and my function is 0.5 raised to the 0.5x plus 4. And I get 17.6. Oh, you didn't see any of that, sorry. Okay, so I get 17.6, right? So I know that that is an overestimate, right? Because if I draw all of these, I'm going to be a little bit higher than I should. Right? So I have those extra bits there. Well, is that enough to make up for that 17.6 being higher than 17.5? Well, I'm not sure. Right? So this graph isn't good enough for me. Right? I'm going to need to go more accurate. So how I can do that is I can decrease the width of my rectangles. Right? And that's what I want to do. Well, I don't need to start entirely over. Right? I can use what I already have here as a base and say, well, how can I change this and make those even more narrow? Right? Well, all I'm ever going to change in order to do that is really this number here, and this number here. Right? Those are the only things that I'm going to change. And really, to type those in is very, very easy for me. So I can make this as small as I want. So I'm going to make it 0.1 as my width. Right? So I'm going to do a 0.1. I'm still going to start at 0. Maybe 0.5 raised to the 0.1x plus 4. And I say, well, how many rectangles am I going to have? Well, if I'm going to 0.1, my distance is 4, right? So here, when I had a distance of 4, and I divided that into 0.5, so 4 divided by that 0.5, I ended up having the 8 rectangles, right? This is a little bit backwards of how we've been doing it, of them saying, hey, you want 8 rectangles, so you did 4 divided by 8, and got, well, there's the distance is 0.5. I'm kind of going the opposite way here. I'm going to say, well, I have a distance of 4, and I want widths of 0.1. How many rectangles do I need? 40. Right, I need 40 rectangles. So as opposed to me going over there and counting 0.1 40 times, I can say, well, if I need 40, I'm starting my count at 0. My count then has to end at 39, right? Because again, 0 is my 1. So I go 0, 0, 1, 2, 3, and so forth, right? So this is going to be 0 to 39. And theoretically, I can make that even smaller if I needed to. But let's try this and see if this is enough to let us know that it's that it's going to hit or it's not. So I'm just going to go up here and copy the same thing. Just change the parts I need. This needs to be now a 0.1. This 7 is now a 39. This 0.5 is now a 0.1. I get 17.399. Awesome. So I know that this is an overestimate, and it is 17.3999. So that is less than the distance, so it will not hit Mrs. Lori. Right? So there's how I can do that. So again, I did that on purpose in a sense because I want you to see, well, how easy it is for us just to make this more accurate, right? And I could go even further, right? If I wanted to, I could say, well, let's make it 0.01, 0.01, and then I got to say, well, what's 4 divided by 0.01? Well, it's 400, right? So I would want to count it up 400 times. Doing that by hand, I would never want to do that. But I can very easily go, well, I'll just make this 0 to 399, type it in, have my calculator do it, and I'm done, right? So you can make those as small as you want. And really, all it just changes is you just type in a few different numbers on your calculator, and you get a drastically more accurate answer. And that's kind of where we're going to try and head here. All right. So real quick, let's head back to this. Let's take a look at problem 132. So problem 132, they give us a very different type of graph here. So this is a graph of months versus dollar or millions of dollars in like profit, right? So let's see, what does the area here mean, right? So the area, if this is millions of dollars and this is time, so it's dollars per month, right? So this is going to be profitable, profitable, losing money, profitable, losing money, and profitable, right? So if I find the areas here, right, and I add them all up, that would be my total profit over this time period. Now, what do I do when it comes down to this part here and this part here? Well, those are negative values or negative y values, correct? So if I do a negative y times a positive x, because my x is still a width of 1, right? I get a negative answer, which makes sense because I'm losing money in those months. So when I add all of these up, positive plus negative plus positive plus a negative plus a positive, right? So these are just going to end up being subtracted from my area because they're underneath that x-axis. And that's the big thing that you want to kind of keep in mind as you go through number 1, 3, 2. So if you haven't yet, go ahead and pause, answer problems A, B, and C, and then we're going to go ahead and move on. All right, so, oops, there we go. All right, so a few notes here. Again, this is stuff we've gone over in the past. If we have a left endpoint rectangle, we're just doing from where the left edge of that bar hits on all those. A right endpoint is where the right edge of that rectangle hits, and we add all of those up. So this is just kind of a formal way of like saying the stuff we've been doing, right? This becomes very important as you move forward. It's just kind of make sure you have a good understanding of what a left endpoint versus a right endpoint looks like. All right, so for our closure here, how do you determine an approximation is an overestimate or an underestimate of the actual area under the curve? So again, you could do this by those rules. Well, if it's an increasing graph, then the left endpoint is going to be an underestimate and the right endpoint is going to be an overestimate. But really, if you sketch the graph and then draw one or two of those, you should be able to very easily see, hey, this is going to be an over or an underestimate, right? And even at a point, there's going to be a time where you really don't even need to draw. You can just see, hey, here is what the graph looks like. Left is going to be an under, or right is going to be an under, whatever it is. All right, so that is it for 324. So here is our homework for 324, doing 134 through 144. And that also concludes chapter 3 for us. So when you finish that, our next thing we are doing is the closure, which is 142 through 151. With that, I will talk to you guys next time.